There's a lot of opposite operations in mathematics. For instance, addition. If you start with 5 and you add 2, you get 7. But then if you take 7 and you subtract 2, you're back at 5, because addition and subtraction are opposite operations. Same with when you multiply two binomials here. If we multiplied these two binomials, we would get this. The opposite of multiplying that out would be factoring it. And so by factoring this, we would end up with our two binomials. And similarly, we could look at sine theta equals a ratio. If you take the inverse sine of the ratio, you're back to your angle. So sine and inverse sine are opposite operations. So then it makes sense that since we've been taking all these derivatives, let's just say we're going to take the derivative of x squared with respect to x. We know that the derivative of x squared is 2x. Then we should be able to start with 2x and somehow go backwards to x squared. And this is what's called, so this is called a derivative. And then what we are going to look at is the antiderivative. So what the antiderivative would say is if we started with 2x, what would be the function that we would get so that when we take the derivative of it, we get 2x? And of course, that's just x squared. So the antiderivative of 2x is x squared. Why? Because the derivative of x squared is 2x. So going this way would be a derivative. Going this way would be the antiderivative. Now another word for antiderivative is called the integral or integration. And how we would express this is usually with kind of a stretched S shape, an integral symbol like this. So we would say the integral of 2x, and then after that, we need to let people know what the variable is that we're integrating with respect to. So just like when we're taking the derivative, we would have the derivative of something, and then down here we usually have with respect to x. Same thing with the integral. The integral of 2x dx equals, and what we're asked to find here is what is the function such that when you take the derivative, you would get 2x. And of course, that would be x squared. Why? Because the derivative of x squared is 2x. Let's just do a couple of more here. Say we had this one, 5x squared with respect to x. So we'd have to ask ourselves, what would the derivative of this be? Or what would be the original function such that when we took the derivative, we would get this? Well, there's a constant term here, this constant term 5. I could take that constant term and move it outside of the integral so that I'm just looking at the integral of x squared with respect to x. And you remember when we took the derivative of something, say this was x to the power of 4, if we were asked to find the derivative of this, we would put exponent down in front and reduce it by 1. Well, when we have x raised to a power, when we're integrating, we would need to add 1 to the exponent and then divide by the exponent. Oops, I've already integrated. So when we're integrating, we add 1 to the exponent, and then we divide by the exponent. And so we would end up with 5/3 x cubed. Now the great thing about this is it's easy to check your solution. So all I'd have to do is take the derivative of this and make sure that does it come back to 5x squared. So let's see, if we took the derivative, the 3 would come down in front, but that would just cancel with this 3 below, so we'd have 5x squared. So yeah, the derivative of this would equal this. So we can summarize, if we are taking the integral of x to the power of n with respect to x, this will be x to the power of n plus 1. We have to add the exponent and then divide by the exponent. And the reason why that is because when you're taking the derivative of this, we would bring the exponent down in front, but we need that exponent, that coefficient now, to cancel with something in the bottom, because there is no coefficient of n plus 1 here. And then when we subtract 1 off the exponent when we take the derivative, we would just have n. Now, there's one other thing that you need to remember when we're taking the integral. Let's go back and we'll look at this one again, the integral of 2x. So I said the integral of 2x with respect to x was x squared. And that's in some ways correct, because the derivative of 2x is, the derivative of x squared is 2x. But there are other functions similar to this, such that when we take the derivative, we would still get 2x. For instance, if we were asked to take the derivative of this function, this is also 2x, and the derivative of this function is also 2x. So when we integrate a function, it's possible that there is some constant, some number at the end here. We won't know what that is, but when you take the derivative of a function plus a constant, that derivative is 0. So when we integrate, we must always write a plus c here, because we don't really know what this number possibly would be at the end of the function. So what I should have done back on these ones is when I integrated 2x with respect to x, I could say for sure there's an x squared in there, because that's the only way to get 2x when we take the derivative. But there could be some plus c. There could be a constant here of some kind. I just don't know what that is. And so same with this one, the integral of 5x squared. Yes, it's 5/3 x cubed, but again, there could be some constant at the end of this. I just don't know what that is. And so also in this formula, we would have a plus c at the end after we have integrated. Let's look at some examples here then now. The integral of x to the power 7 dx, well, we know that we would add 1 to the exponent and divide by the exponent plus c. So a very simple one. And we can check our answer by putting the exponent, taking the derivative. So 8x to the power 7, but the 8's would cancel out, so that would just leave us with x to the power 7. And the derivative of a constant, of course, is 0. So that one's fine. And then here we have a polynomial, 3 terms, a trinomial. And so we can really just integrate each term separately here. So this would be add 1 to the exponent, divide by the exponent, minus 7. This is x to the power 1, so we'll add 1 to the exponent and divide by the exponent. And then this is like, if you have a 5, of course, that's like 5x to the power of 0. So now that's 5x to the power of 1 divided by 1, which we don't need to do, plus our constant. Don't forget plus c. We can tidy this up a little bit. And quickly checking our answer, 3x squared, good. Minus 14 divided by 2 is negative 7. X, good. The derivative of 5x is 5, good. And the derivative of constant is 0. So that one's good. Let's look at a couple more, a little bit more complex. So here we have the 5th root of x squared. But remember, we could always write this as an exponent. So x to the power of 2/5 with respect to x. And now I can use my shortcut method by adding 1 to the exponent. So 2/5 plus 5/5 would be 7/5. But then I have to divide by the exponent and do a plus c. And x to the 7/5 divided by a fraction is the same thing as multiplying by the reciprocal. So I'd have 5/7 x to the power of 7/5 plus c. And putting this down in front to check our answer, that would cancel that out entirely. X to the power of 2/5 when we subtract 1, which is what we've got. And then this one is similar. This would be x to the power of 1 times x to the power of half, which is x to the power of 3 over 2. 2 over 2 plus 1 over 2 is 3 over 2. And so now I can actually take the integral because I have a single base with an exponent. So we'll add 1 to the exponent. Becomes 5 over 2. Divide by the exponent, 5 over 2. And then multiply by the reciprocal. So 2/5 x to the power of 5 over 2 plus c. The integral of x to the 7 minus 2x4 plus 3 divided by x squared. What I could do with this one, we're not at the place where we can have any quotient rule when we're integrating, but I can divide this, x7 divided by x squared, and call that x5. And then this would be 2x squared, x4 divided by x squared. And what I can do with this one is I could bring this up to the top and write that as x to the power of negative 2 with the 3. So I've got the exact same expression here. And now I'm ready to integrate. So add 1 to the exponent, divide by the exponent, add to the exponent, divide by the exponent, add to the exponent, divide by the exponent. So add 1 is now negative 1. And then I can write this as x6 divided by 6 minus 2/3 x cubed minus 3 over x, because x to the minus 1, we'll put that in the denominator with a positive exponent, plus c. And then, of course, we can do the integral of some trig functions. What's the integral of sine x with respect to x? Well, remember, we know that the derivative of, we know that the derivative of cosine is negative sine. We know that the derivative of sine is cosine. We know that the derivative of tan is secant squared. So that must mean that the integral of negative sine x would be cosine x, the integral of cosine x would be sine x, and the integral of secant squared would be tan x. So I don't have sine x here, I have sine x here, not negative sine x, so the integral of sine x will be negative cosine x plus c, because the derivative of cosine is negative sine, and the negative would make a positive sign. So we can go backwards and integrate each one of these things and get what our derivatives were. So this one here, what's the integral of secant squared? Well, if the derivative of tan x is secant squared x, then the integral of secant squared x must be tan x, because the derivative of tan is secant squared. And this is an easy one. What's the integral of e to the x? Well, we know that the derivative of e to the x is also e to the x. So the integral of e to the x will simply be e to the x as well, plus c. And again, you can always check your answer by taking the derivative of this and make sure you get this. Of course, the derivative of e to the x is e to the x, and the derivative of a constant is 0. Here's a common mistake that people will make when they're integrating this one. Lots of students will do this. They'll say, oh, this is the same thing as x to the minus 1. And then they'll say, okay, so I add 1 to the exponent, and then divide by the exponent. And then it's like, I don't know, let's just call this 0. So we'll go 0 plus c. But of course that doesn't work, because the derivative of 0 is 0, and the derivative of the constant is 0, and we're certainly not getting this. So you remember that the derivative of ln x is 1 over x. So then the integral of 1 over x must be ln x plus c. So this is the only one where adding to the exponent and the dividing by the exponent won't work, because it's the derivative of ln x that gives you 1 over x. Let's look at this as some functions. Let's say this is back to what we were doing before when we were doing derivatives. So if we started with this function, f of x equals x squared, we knew that when we took the derivative and got this, that this represented our slope. It was the slope of the tangent line to this curve right here. So what if we started with this function here, f of x equals 2x. So say we just started with f of x equals 2x. You were given a function like this, and you were asked to integrate this function. Sometimes what we do, instead of a little f of x, if we're integrating, we'll use a capital F to represent the integral of this thing. So if we integrated this function, we would get x squared plus c. So the integral of this function, x squared plus c. We don't know what that constant term is. So if we were asked to graph this function, let's get some grid lines on here. We know that this is the parabola, but the problem is, what is the constant term? So if the constant term was 0, the parabola would look like this. But we don't know what the constant term is. Maybe the constant term was 1. Then the parabola would look like this. Or maybe it was minus 3. Maybe we had minus 3. And now our parabola looks like this. So this one would have been y equals x squared minus 3. This one was simply y equals x squared, where the constant was 0. And this one in here was y equals x squared plus 1. So you could imagine if we were asked to graph this, there would be all of these parabolas all over this graph. Yet, at any given point, say when x is 1, the slopes of the tangent lines at each of these places is going to be identical, because the derivative of this function is always 2x. So remember, this here is now representing our slope. So here's our original function, x squared plus c. We integrated to find that. And here's the slope. So when x is 1, we know that the slope is going to be 2 times 1, which is 2. So the slopes of all these lines here would be 2, regardless of what these functions look like, whether what the plus here was, what the constant term was. And at 0, obviously the slopes for all of these ones, when x is 0, is going to be 0. And then if we go to negative 1, the slope is always going to be negative 2. And so what we could have is we could really have all of these kind of little slopes plotted on here. And then when x is 2, the slopes would be 4. So they would be steeper yet when x is 2. And so what we can have on our sketch of our integral curves, because we can't actually know exactly what this constant is we could have all these different graphs plotted, or we could do all these slope fields. They're called slope fields when you have these little dashed lines representing what the slope would be at any given point on our coordinate system. And obviously as x increases, these slopes continue to get steeper and steeper and steeper. And same thing on this side. So these sketches, these three graphs that I drew here, would represent the integral curves. These are the graphs of the integrals, again not knowing what the plus c would be. I could have drawn more on here, but I just drew three. And then I started to draw what the slope fields would be if we looked at the slopes of all of these different integral curves on our graph. So those are integral curves and slope fields for this basic function f of x equals 2x, which when we integrated got x squared plus c. Well, you might be wondering, how can I ever find out what c is, what that constant term is? And the only way that we can do it is if they give us a point on the actual integral curve. So they might say f of x equals 2x, and they might say when x is 1, y needs to be 3. So okay, now I can integrate this function. The integral of this, of course, is x squared plus c. And now I can say, okay, when x is 1, y should be 3. So I can substitute in 3 for my y value, 1 for my x value, and then subtracting 1 from both sides will tell me that c should be 2. So now I can say, okay, the integral curve that you're specifically looking for is the one x squared plus 2. So now if I were to go back and look at my slope field, I would know that the one that I need to be looking at is the one that is at plus 2, which would be this one. So the only way we can solidify which of these integral curves is the correct one, or the one that we're asked to find, is if they actually give us a point on the integral curve. It's the only way we can find out what c is if they give us a point. We'll look at one more example like that. So let's say we know that dy dx equals cosine x, and we want to know what is the solution to this initial value problem. So when x is pi over 6, y would equal 2. So we will integrate this function, the integral of cosine x with respect to x. And we know that the integral of cosine x must be sine x plus c, because the derivative of sine x is cosine x. So we would end up with y equals sine x plus some constant. Now in order to figure the constant out, we need to put our x value in here and our y value in here. So we get 2 equals the sine of pi over 6 plus c. Now the sine of pi over 6, that's one of our special triangle angles. So it looks like the sine of pi over 6 would be 1/2, opposite over hypotenuse. So 2 equals 1/2 plus c, and then subtracting 1/2 from both sides gives us 1.5, or 3 over 2. So we can say that the function would be y equals sine x plus 3 over 2. That would be the original function, ensuring that it went through that point on our integral curves.